Jersey.
Happy to be back. This is awesome.
Falcon Space, so we got a lot of new toys here for you. Starting off with a new air conditioner.
So hot. This is gonna feel so good. Oh my god. It's already like 85 degrees outside. Inside here it's like less than 65.
Yes, it's really nice. It's really nice.
Dude, you cleaned up.
This isn't even fully clean yet. We have a couple more things to do, but we're gonna be taking some professional photos later, and try to just showcase the lab. I want pictures that will go on the website that will get people to say wow, like real photos.
Yup.
So we started off. We got an air chiller, which basically removes the dehumidifies the high pressure air system. This is stuff that we got from Drew, this glass bell jar.
Smokes, that thing is big.
And this protects you from the near
The shattering explosion.
the shatter implosion explosion that can happen with glass, which is something that they didn't mention on the call. They should have mentioned how this can literally explode at a high power.
I want to put a little something in there. I don't know what that means.
This is some Mu metal that
Oh, that's the new metal.
that's from Todd. Yeah.
Oh, it's so big. It looks like 2 rounds of that. Oh, that is a lot.
Mm-hmm. It's a couple $100 worth, he said.
Yeah, easily. That is awesome.
So this over here, this is something that Drew gave me. So what this basically is you stick this inside the vapor depth chamber, and you hook up to the high current, low voltage system. And the shorts over here get super hot, and you could have a sample in the center where it gets, vapor deposited evenly.
Yeah, you can see the line on it from where he's been using it. Had like a wire or something going over it.
Yep. And we got 2 of them.
Oh, wow.
And a whole bag full of spare parts over there. So we got a whole bunch of new toys. But vacuum pump too. This is our other vacuum chamber. But this is what you came for, right?
All the RF goodies.
But this is what you came for. This is the S-band setup from George Hathaway.
Gotta connect that.
Yeah, that's a camera. I might swap it out with something else.
Dude, this thing's built pretty good.
A lot of thought went into it. When you realize the complexity of what he built here, it's in many ways it's overkill. But I say that it's overkill because they never really finished the project. They never ran the experiment.
Oh.
They did
Built all this and never experimented with it?
Yeah.
Oh my gosh.
They never ran the experiment in this system, which is insane.
Yeah.
When you see how much work they did.
All the engineering without any of the play.
And you haven't seen everything. So on this side, you got the vacuum setup. The roughing pump for this is out under the table over there. Hose pulls in the roughing vacuum.
Oh my gosh.
This is a turbo. This is a turbo. And then there's a high vacuum valve.
This is the seal that you guys were working on getting, right?
No, it's a different one, but similar size. So what's happening over here, it's going to this bellow, and he has contraction suppressors. Basically, when you pull a vacuum on these like bellow things, they tend to contract.
And you lose your seal.
No, you don't just lose your seal, but it creates a pull. Like everything wants to go closer together, and if you have things that are stiffly in place, something's going to give. So he put these suppressors on there that keep a constant pressure so you can counteract that. They thought of everything. Now, this is on here right now, but you can't really see this, but in here is where the magic is happening.
I see the micrometer there. Your adjuster to be able to move the sample as needed.
Yes, exactly. That's exactly what this is. This has, I think, 4 gauges on it. You can turn it left and right. You can go X, that's like in and out. You can go Y, which is left and right. And then there's Z down here, which is up and down. So there's an armature in there that's holding the scale, which is the head of a thermogravimetric analyzer, a very super sensitive scale. There's a whole armature that can move left, right, up, down, and twist.
So you have 4
and in and out.
4 stages. You have translational, 3-direction translational, and then rotation, 1-direction rotation.
And there's also in and out.
Yeah, that's translational. X, Y, Z, and then roll.
Yeah. And all of that in vacuum, while maintaining vacuum. This setup alone, I don't know where he got it from.
That is a really unique setup. I haven't ever seen anything where it's all like nested in like that.
Yeah, there's a turn over there there's 4 separate rollers on it. This roller obviously turns the entire thing on the inside.
Can we open up the chamber there so I can see what it looks like on the
inside? Yeah, let's do that. Let me move this over a little bit and give us a little space. So to open it up, we got these little neat twisties, hand twisties. Or you could do that one on that side if you like.
Oh, and it's on this rail, so it all slides.
Yes.
Oh.
Yes.
They thought of everything.
They thought of everything except running the final experiment, which is just crazy.
They were building this for the experiment, for the DNO experiment, right?
Yeah. He said that they ran out of money for the liquid helium, and that there was a loss of interest or something like that.
So like 99% of the way there, and you got these 2 guys?
Yeah, those guys. Okay, that's going to be a flathead screwdriver. Guess this one we'll have to do. Wonder. I don't think there's any vacuum pulled on this right now. What's it say
We're
there?
pretty close to 0. We're at like -2 inches of mercury, which would be a vacuum, right?
Oh, there's a vacuum in here now?
I think so.
That would be pretty cool if it's holding a vacuum. No, there isn't.
Okay. Oh, that is cool. Oh, that is cool.
So this armature has 4 degrees of motion, and it's moving the scale. This is the super sensitive scale where everything happens. I see stuff turning on my side here.
I see this guy here turning.
This is turning too from that.
Okay. We got that guy. That's turning that one for. Okay, so that's your Z. That's your in and out. That is your left and right. So that's your. Oh, they're even labeled.
Y.
You got your
No,
X.
They're not just labeled; they're like engraved with the label.
Y.
And there's another one.
You got your
There's
Z. There's the Z. Oh man. All right, so the sample goes inside here, right?
no. The sample goes on a stick that attaches to the end of this.
What's going on with all this guy? What's all this then?
So this is the head of a thermogravimetric analyzer.
Oh, that's how you're actually taking your measurements.
Yeah, so it's on a stick that goes into a tube over there, a glass tube that's going to be held under vacuum, and we can include cryogenics with it as well. And that reminds me, actually, we might want to run and go get the liquid nitrogen now. If we're going to do this under cryo, we might want to do that now, because otherwise it's going to have to wait till Monday.
Yes. That will give us more testing time, hopefully this weekend, assuming we get all set up.
Yeah, and we could also play with it and do other stuff with it.
This guy looks really sensitive.
It's really sensitive, and it might have been broken already because we were screwing around with it. But we do have spare parts over there. We have spare. We can replace the entire head.
It doesn't look too terribly difficult to at least just test it to see if it's...
I haven't tested it yet because the cable for it was...
it's 2 wires.
It's actually a ton of wires here.
Oh, it's this whole bundle?
The whole bundle connects to it.
Oh, geez. Well, that bundle is all going up here.
Yeah. So what happens, all these wires connect to it, and they go into connect a vacuum port over there. And there's a custom wire that goes up to this auto balance weight suppression thingy. And what I wanted to do is take the output of this module over here, this box, and feed it into LabVIEW so we can chart it. But what they were hoping to look at is these little, this was their reading. This would have been the reading for the entire experiment.
I see something questionable. They may not have thought of
wire management. This was something that we did.
shielding is what I was going to say.
Shielding, yeah.
So normally you would have like a metal sheath around this that's grounded, right? And so any transient currents, any stray currents you get from the RF just get shunted away and don't feed into all these wires that are going to your very delicate sensor.
That's a very good point. We should... well, this entire chamber itself, this thingy acts as a Faraday cage.
Yeah, but you got RF bouncing around in there.
No, it's not bouncing around in here. It's going through a very small hole.
Because the stick goes through a hole over here. Okay.
Yeah, the stick, it's basically sitting at the end of a test tube. So the sample doesn't really have that much.
And the microwaves going this way.
They're going this way.
They're going.
The magnetic field is going this way. Electric field's going this way because this magnet is vertically polarized.
So some RF could get through the hole, the stick hole.
I don't know. It's at S-band. Take a peek in there. Can you see the hole?
Okay, yeah, I see.
I don't think much S-band is getting through that.
I mean, S-band, you're like 9 centimeters is the smallest.
Yeah, that's not much is going to get through that hole.
And that's like maybe 1.
Yeah, that's about 1 centimeter.
So at most you're getting like 1, maybe an 1/8 wave. You might get 1/8 wave through there.
So basically, this setup is geared for mass testing of the Alzofon experiment. In vacuum at cryo. And it pulls back all the way to here, so you can have your test thing. The sample would be somewhere around here. On the end of a stick, I have a whole bunch of those super fine sample holders. And you turn this on. It's supposed to do something to the scale to keep everything held in place.
Where's the control for the magnet?
So the control for the magnet, we're going to have to just use the same one that we're using now, the same power supply. I didn't want to get a separate, because the power supply is already hooked up to LabVIEW, so I kind of want to just keep things the way they were.
But they're different magnets, so...
It's just the same. It's 2 wires, that's all it is, just current.
Any idea ballpark on the spec for how much current this guy draws? Because it looks bigger than your... Well, it looks wider, not thicker.
Well, we checked it. It's less than... It's sub-ohm. So, so voltage is not really a very high component of it. But they did run that part of the test, and he told me it was drawing less than 100 watts.
Oh.
It's a very... This magnet can go up to 3 Tesla, but at the field we're doing it at the field of I think 0.1 Tesla or 0.09 Tesla.
Oh, geez, yeah, okay.
Okay, there is 4 fundamental types of spin that we're dealing with. First one is, and this is starting from more fundamental going up to larger things, subatomic spin. So by subatomic spin, we are talking about protons, neutrons, and all the things that are in the nucleus of the atom. Now, these coalesce together, they amalgamate and become nuclear spin. Also, this is what happens in NMR. We energize the nuclear spins, and as the energy is removed, it sort of pings back a frequency, and that tells us, hey, this is a hydrogen atom, this is a boron atom, so on and so forth. That's how MRI machines work. Third one, call this electron spin. The electron spin. There's many different types of electron spin too, but we'll just simplify it. Electrons are on the outside of the atom. These are what are excited via electron paramagnetic resonance. And then we have the fourth one is molecular spin. Now, molecular spin is what nuclear magnetic resonance is usually meant to study, because you're dealing with several atoms that are connected together. You want to figure out how they're connected, what particle that is, what molecule that is, whether it could be biologics. You know, that's where most of the money is in studying molecular spin. Although molecular spin is not of any interest to us, because over here, we're mostly interested in subatomic spin. Subatomic spin orientation is anti-gravity. That's where you break the bonds of angular to linear motion that becomes momentum. That is the effect of inertia. This is where the magic happens in the subatomic spin level. In the nuclear spin level, there's not much happening. But this subatomic spin orientation affects the nuclear spin response, because nuclear spin is built up of subatomic spin. So the more subatomic spin orientation, a proton to proton and neutron to neutron spin alignment, the more coherent the nuclear spin alignment becomes. Now, the way to achieve this spin orientation is through electron spin jiggling. So by energizing the precession of the electron spins, we're able to orient the subatomic spins. Because the electrons are basically orbiting way outside of the nucleus, but they're connected, because they're negatively charged, they're connected to the positively charged protons in the core of the atom. So they're really, you know, there's a proton that's pretty much, the opposite of every electron in there, and they're playing around with each other. That's why they're so tightly bound in. By changing those spins, by energizing them in various different ways, you're able to affect the subatomic spin. Now, how do we do that? Well, the way to affect electron spin, which is where all of this starts, all of the other spin features all start with the electron spin. Now, electron spin orientation is an effect that everyone knows. It's called magnetism. When you have a magnet, all you're doing is orienting the spins of the electrons. Everything around it would, that's why north and south of an electron, of a magnet, act the way they do. They're really just, let's say they're just rotating in this direction. So if you look at it from the bottom, you'd see clockwise. If you look at it from the top, you'd see counterclockwise. It's all about your perspective and how you look at that same spin. So when you apply another magnet that's spinning in the same direction, from this perspective I'm seeing counterclockwise, but from this perspective I'm seeing clockwise. That's why they don't want to match together. But when you have them opposite, they want to attract, because from their individual perspectives, they're actually spinning in the same direction. That's why north and south magnets work the way they do. You know, north to north pushes apart, and north to south wants to attract. So we start off with a magnetic field that orients the spin, and the degree at which the spin is oriented is the magnetic field strength. So theoretically, there should be a higher upper limit to how strong a magnetic field can get. When you orient the electron spins, you get something called Larmor precession, and my marker is done. You get Larmor precession, which is essentially the axis of rotation of the electron precessing around. So let's say it's spinning nicely like this. Now it's spinning nice like this. Now the Larmor precession is always happening. Everything around you has these precessions, these spins, the subatomic wobbles are always happening. But when you apply a magnetic field, you suddenly orient it, and now you can start playing with it. So the stronger the magnetic field, the higher the Larmor precession. Now, the rate at which the Larmor precession relates to the magnetic field is called the gyromagnetic ratio. Gyromagnetic ratio. Now, for free electrons, it is about 28.025 gigahertz per Tesla. Tesla has a magnetic field strength that's pretty strong. Most neodymiums do not reach 1 Tesla. Usually about half a Tesla tops, and that's a really powerful neodymium. But yeah, at 1 Tesla magnetic field, you'll be dealing with 28 gigahertz Larmor precession for the electron spin. Now, if you're able to energize it at whatever this ratio gives you, it's plus or minus. This is for free electrons. When they're bound, it's slightly different, but it's not much more than, it's between 27 and 29 gigahertz. It's in a very small gyromagnetic ratio. I think Michael Prone did the math on it once, and it came out to literally very close, just for aluminum. And that's because the only other thing that will change it is its hyperfine coupling. So the hyperfine coupling is the connection between the electron spin and the atomic spin are connected by the hyperfine. So the hyperfine coupling is what connects them together. The way to transfer the orientation is by pumping up the electron spins and then giving it time to relax, and during that relaxation period, it transfers its orientation to the core. The known use of that is by orienting the subatomic spin to spin, like the protons to protons or protons to neutrons spin, so that they're all kind of wobbling together rather than roughly wobbling together, is the nuclear spin suddenly becomes more coherent. When the nuclear spin becomes more coherent, the ping that you get back when you're doing NMR becomes a lot stronger, hence you get a stronger signal-to-noise ratio. Nuclear spin orientation, or actually it's not really orientation, it's nuclear flipping and or resonance, happens at a totally different gyromagnetic ratio. It's way less. It's about 1,000, 0.1,000 of what the gyromagnetic ratio is for electrons. So you can just apply a magnetic field, and with nuclear spin, you're able to energize it in about the megahertz range, and you're basically energizing the spin of the entire atom, the wobble of the entire atom. And then when you take that away, it pings back in RF frequency that you're able to pick up. And that also works with molecular spin. The problem is with molecular spin, though, is that the signal-to-noise ratio for molecular spin, because you have several atoms that are not really coherently spinning themselves, combined together now, and you're trying to get a ping back from that, that's not going to ping very strongly, right? And this is where the money's at, because big pharma and the medical fields all want to know what's happening on the molecular spin. So this is where the industry momentum is headed. This is where what everyone is. When we were at Sillimer, everyone was concerned about number 4. What we're concerned about is number 1, which is what they actually use. It's an effect they use in order to figure out what number 4 is. Because without number 1, you ain't going to see number 4.
So with the dynamic nuclear polarization that you're working with, is that affecting electron spin and in turn affecting subatomic spin?
Yes.
Okay.
Yeah. But there's other ways to do it. Subatomic spin can also be achieved by that Razer effect that they talked about, and it's possible counter-rotating magnetic fields might affect it too. I don't know, but
What's the Razer?
Razer effect, it's this weird thing that they do with liquid helium, hydrogen. They pour it on iron oxide, and the liquid hydrogen becomes polarized on the subatomic spin level. And then they're able to use that, because subatomic spin, like I told you, it is like a magnet that it affects everything around it. So all they do is pour liquid hydrogen on the sample, and suddenly the nuclear spin in that sample, or the molecular spin if it's a molecule, suddenly becomes greatly enhanced, and then they can do NMR on it.
That makes sense because
So it's a much cheaper way to do it.
the liquid helium is acting
Hydrogen.
liquid hydrogen is acting all as a single wave function, so it has one spin. It's got one singular spin to it.
Yeah.
It's a macroscopic quantum effect, right?
Right.
And so now you're bathing your sample in this macroscopic quantum effect, right? So it's automatically going to want to couple with that, right?
Yeah. And now another interesting thing is subatomic spin. In certain materials, it's the relaxation time for it is different. Xenon gas, in particular, has an extremely high, long relaxation time, measured in tens of minutes. So
So it reaches that forbidden transition, and it stays in that for minutes.
I'm not sure how they orient. I think they usually use Razer to then affect the xenon, and then they feed you xenon intravenously, and they're able to do NMR things in vivo. Like that's what people were doing at a SOMAR, which is crazy. Yeah, they're using a spin to affect the spin to affect your body, and xenon is non-toxic, so you just it's fine. It'll go in, it'll absorb a little bit, and come right out. Yeah. My handwriting sucks. But it makes sense?
It makes sense.
Yeah, thank you, Mark. Thank you.
Now, the main issues you've been having with these setups is I don't know how much energy is actually bouncing around in that chamber, or you have to. We need to figure out how to measure the Q factor of the chamber, and we need to make sure the energy is hitting the sample rather than bouncing back towards the amplifier, and it also has to be pulsed properly, which is why we got that pin diode.
All right, I'm starting to get that we need to do some basic calibrations of our RF arena over there. If we were gearing towards a specific calibration, what we are trying to measure is we are trying to measure at the sample, right? We're trying to measure at the sample the change of this guy, which we're not going to measure that. We're going to measure from here, right?
How we're measuring it by seeing its weight change.
But there should be some RF way of knowing that you're doing what you want to do.
So one way of knowing that you're doing what you want to do is when these things are happening, when this is being transferred to that, the sample is absorbing energy.
So your amplitude, your reflected amplitude is going to go down.
Yes.
Okay. That is what I needed to know, because that is what I am calibrating for. I'm calibrating to minimize our reflections in the first place, and then maximize the sensitivity of that reflection reading.
Well, that's if we wanted to get a spectroscopy reading out of electron paramagnetic resonance. If you wanted to get a spectrum of it, and we can do that. The lab view and everything is geared up for that. We have two separate spectrum analyzers that are hooked into LabVIEW, that it just reads the peak value of each pulse and feeds that into a chart. So we can get that. We can get that data.
Because
We're trying to get a finely tuned system that you can tune it when the sample's put in. You know, you can change something, you know, there's levers and stuff to change, get it finely tuned, and then when you go through electron paramagnetic resonance, you're able to see, oh shit, reflections suddenly dropped off, let's stay here. And then we're seeing something, oh, weight's dropping, weight's gaining. You know, that's what we want to do with that setup.
So we need to do frequency sweeps until we find the frequency that it starts oscillating well at, and then we need to start optimizing our pulse times to optimize how much energy it's absorbing, right? How deep we can get that dip, right?
Mm-hmm.
Hopefully, we should be able to find association in the data between the level of that dip and the amount of the weight change.
The thing is, it's happening at hundreds of hertz, hundreds of times per second. The scale only gives us 4 samples a second. I know. That's how it is. There's gotta be a better scale. Well, you know what? That's what we have right now. There is a better scale. There are better scales, but you know what? It doesn't matter. Yes, you can get a billion times a second if you wanted to, but that would be another month of lab view and hooking something else up, and you have to do all the RF shielding and everything. And you know what? It doesn't matter because you're not looking at it that fast, anyways.
I don't want a single sensor to be our single point of failure, right? So if you're going through
We have a secondary scale with a dummy load on it, just to make sure that we're not getting false readings from the environment. But there's no way you can't hang the sample from 2 scales. It has to be 1 scale.
Yeah, no, I'm not saying have a second scale. I'm saying have some electronic means of your RF measurements to be able to go, that's my signal that means I'm doing the thing I want to do, and here's my physical measurement of the
That's why
Right.
we have the RF, the spectrum analyzers, signal, giving us a signal, giving us a reflected power reading.
But if we're operating in standard temperature in vacuum,
This is not vacuum. This is a standard temperature in air.
standard temperature and pressure. So if we're doing that, the lifetimes of those forbidden transitions are very, very short, right?
Mm-hmm. That's why we're operating in hundreds of hertz. By very short, I mean milliseconds, not microseconds or nanoseconds.
So we're certain that our scale is going to be able to pick up these changes.
No, they're cumulative. We don't expect it to pick up every single change. It's cumulative. Every time you do it, it goes up, some way.
It's going to go up, and then it's going to lose a little bit, and it's going to go up, and it's going to lose a little bit.
But that's happening at 400 times a second. Or 200 times a second, something like that, yeah. Even if we had a high-speed scale measurement, you'd have to read it on an oscilloscope and have to be there live. There's no way we're collecting that much data. There's a limit to how many lines of data you can put inside of an Excel sheet. We actually had to desensitize our data reading because it was just overwhelming the Excel files.
Yeah.
Yeah, but in the Alzofon paper, you're getting to something important. They did measure the scale data in a very fast manner, and they claim that they saw weight changes on the order of when the pulse was turned off. That's when they saw but that would require a high level of sophistication, and it's possible all they were seeing was RF energy interfering with the scale. That's because I've seen that as well. We had to change scales in order to get away from that and shield the scales properly. So things to consider. Anyways, did it give you a better idea what's going
It
on?
gives me a lot better idea.